Okay, this is the second part of the replacement lecture recorded for MAE 3323 Tulsa on October 14th of the year 2011. In the earlier video that I've asked you to watch, I did a quick coverage of the Castigliano notes that half the class missed because they left early after the test. You can tell that sort of bothers me a little bit. But those folks will be able to read the textbook and the notes very, very carefully to get caught up. Now that I've sort of talked about the big ideas, and there are three of them, and I'll summarize those three big ideas. That first of all, structures have energy. Castigliano says we can take derivatives with respect, partial derivatives of the energy with respect to a load, and that can allow us to calculate deflections. That's the first big idea. The second big idea is if there is no load at the location where we want the deflection, we can apply a dummy load and do pure Castigliano, but at the tail end, or maybe earlier, we can set that dummy load equal to 0, and we can calculate the deflection of a structure where there is no load. And then the third big idea is when we have indeterminate structures, which is really too many loads to be calculated from statics. We can take one of those extra reactions, or one or more of the extra reactions, and calculate those reactions, not using statics, but using the beam deflection equation. And Castigliano says basically treat the support as an unknown load. Replace the support with an unknown load, and then calculate the deflection because of that unknown load and all other loads, but then set the deflection equal to the proper value. In many cases, the purpose of a load is to keep the deflection equal to 0. So we would then set that deflection equal to 0. We do have some examples where there are other things happening. So what I want to do now is start doing the calculations for Castigliano and go over them very carefully on some example problems. I am going to use MathCAD to do it, and I'm going to slowly teach you to build up your MathCAD skills, or at least the reading of MathCAD. I'd like you to be able to read MathCAD. So here is the simplest Castigliano problem that says let's calculate the deflection of a cantilevered beam with an end load F, and I want to calculate the deflection at the point where the load is applied. Now, this picture came from Appendix 9 in our textbook, and it does reveal to us that this cantilevered end does impose a reaction here and a moment here. And I'm going to choose to do the easiest formulation of this problem by choosing to measure my x variable, because I need to write the moment anywhere within the beam as a function of some variable x. I'm going to choose my x variable equals 0 and heading toward the left. If that's the case, when I integrate across the beam or write my equations across the beam, I'm going to stop when I get to this wall, and I'm never going to say anything about these internal reactions. A slightly harder version of the problem would be to let x equal 0 at this cantilevered end and write moments with x increasing as I move away from the cantilever, and then I'm going to look left to write my moment equation. To do that, I would have to involve this moment and this static reaction. I'm not going to do that in this simpler version. My x will be measured from the free end, increasing x as I move to the left. Now, this is the deflection equation, y is a function of x, that came out of the appendix, and this is the y max. This is the max deflection equation, which does occur when x is equal to L, because the book measures x from the left-hand end. So when x is equal to L in this equation, we get our maximum deflection. Okay, and we also, I wrote down my bending Castigliano deflection calculation, which says, first of all, go ahead and take the partial inside the integral before you do the integral. So the partial of our energy with respect to the load F is an integral 1 over EI m partial of m with respect to F dx. That's our bending energy. Now, here's the MathCAD. Moment is a function of x. Anywhere within this beam is equal to F times x. If I'm talking about cutting the beam right where my mouse is, x is my distance from that load F. My moment is F times x. Now what I can do is take my partial immediately, not wait for energy. I'm going to take the partial of the moment with respect to f, and the partial of fx with respect to f is x. Now, my deflection equation is going to be an integral 1 over EI times this stuff. But if I bring EI to the other side, just to get rid of it, then I could call this left-hand side E times I times delta is equal to an integral of something that no longer involves EI. It just involves the moments. That's typically the notation I'm going to use. And so I'm going to say that EI delta is the integral from 0 to L of my moment as a function of x times my partial of my derivative of the moment with respect to f dx, and the integral occurs and I get an FL cubed over 3. Now what's going on here? And I guess I will go ahead and do this one live for a moment. I'm not going to do that for most of these, and so I want to find my integral palette. So I'm going to do this, the integral from 0 to L of the moment, which is f times x, no, f times x. I'm not typing well. Okay, that's the moment. And notice the partial of m with respect to f is just x. So that's times another x. And that's an fx squared dx. Now, when I integrate fx squared dx, I'm going to get an fx cubed over 3. But then when I plug in the L for x, I'm going to get an FL cubed over 3. Exactly what I got right here. If I ask MathCAD to do that calculation for me symbolically by using the symbolic palette and saying please calculate, click away, FL cubed over 3. Okay, and so my EI times deflection is FL cubed over 3. But if I bring EI back over, then my deflection is FL cubed over 3 EI. And that's precisely the deflection that you probably remember from Strength of Materials and is given in the back of the Shigley book. Now, what we did in this problem is merely calculate the deflection at the end of a cantilevered beam because of load F. We did not calculate the deflection anywhere else in this beam. All we got was that EI delta was FL cubed over 3. Let's use the dummy load idea to calculate the deflection everywhere in this cantilevered beam problem. And so I have exactly the same cantilevered beam problem that I had before, but I'm going to apply a dummy load Q somewhere that's not at the end. Now what I don't have written on there is that, but it's built into my math, is this dummy load Q is a distance A from the end of the beam. So if I could place an A marker right there, I would do that. Now what I'm going to do is I'm going to calculate the deflection in a cantilevered beam because of both F and the load Q, but I'm going to calculate it at the place where Q is applied, and that's a distance A from the end. So if I want, part of what that will do to me is cause me to have, since there are two different forces, I'm going to have two different moment equations. I'm going to have a moment equation that's true from the end until I reach Q, and then I'm going to have a second moment equation that's true after I pass Q. So if I'm talking about in this first region, I'm going to call that region 1. My moment anywhere within region 1 when I make a cut here is just going to be F times X. Again, X measured from the right hand end. So my moment in region 1 is F times X. My moment in region 2 is still F times X. I still have a moment because of F, even though I'm in this region. But then I'm going to have a moment due to Q when I make my cut right here. And my moment arm will be the distance between my cut and the load Q. And that distance will be X, my total X, all the way back to the beginning of the beam, minus the distance of Q from the beginning of the beam, and that's A. So my moment here, my additional moment term will be Q times X minus A. So my moment in region 2 is F times X plus Q times X minus A. Now, since I want deflections at Q in the direction of Q, I'm going to take my partial of moment 1 with respect to Q. dm1 dq is 0. There is no Q there. my derivative of moment 2 with respect to q is just going to be an x minus a. In MathCAD notation, I'm saying there's a new variable, dm2 dq, is the derivative of m2 dq, and MathCAD tells me that that is x minus a. Okay, now just to show you a little bit more, to expand out this m2 thing, m2 times dm2 dq is algebraically this. Multiply this times that, and you get that. But if we, at this point, substitute q equals 0 here, then m2 times the partial is just going to be, with q equals 0, just fx times x minus a. So what this thing says, let's take m2 multiplied by dm2 dq, but let's substitute q equals 0 right now, and it gives us a minus fx times a minus x. Swap these two terms, get rid of the minus sign, and we have exactly what I said we'd have, fx times fx minus a. Using MathCAD to the maximum and using my built-in variable definitions, my total energy is two energy terms, an integral from 0 to a of m1 times the partial of m1 with respect to q, plus integral from a to l of m2 times the partial of m2 with respect to q. This is my deflection term in terms of q. But now I'm also going to take another fairly powerful step, and I'm going to substitute q equals 0, and when I do all of that math, I get this deflection term. Now let's look at it a little bit differently. The same thing is my integral from 0 to a of m1 times the partial of m1 with respect to q. What is that? m1 is that, partial is 0, so m1 times the partial is 0, so the integral of 0 is going to be a 0 term. And then this one is going to be an integral from a to l of set q equal to 0 and take moment of fx. Put it right there. My dm2 dq is just x minus a. Well, a minus x, x minus a, minus sign, it's all the same thing. Do this integral, get this thing, which is precisely what I got with the more high-level MathCAD lingo. Again, I'm going to start just doing some of the more higher-level MathCAD and just trust it to do the integration for me and fill it in, rather than typing out explicitly some of this algebra. But I want you to see it in the early problems, that m2 times dm2 dq means, with q set equal to 0, means set q equal to 0, fx times x minus a. This is fx times x minus a. We get that. Okay, so this is the deflection at the location of load q. Now, what variable did I have that located q? The variable a locates q. As I change a, I can get the deflection at various locations. But a would be a variable measured from the right-hand end, telling me how to locate q. But in the textbook, in the appendix, they measure x from the left-hand end. So I'm going to do a variable substitution, and I'm going to take my EI delta, but I'm going to substitute for a the quantity L minus x. That's not a 1, that's an L. Okay, so if this quantity is a, right here, and this quantity is some variable x, then let's see, when x locates q from the left, a locates it from the right, then x is equal to L minus a. Doing that substitution, that says take my deflection equation here, but everywhere I see an a, substitute in L minus x. Do that algebra. Simplify it a little bit. The equation I get is fx squared times x minus 3L over 6. If I go look at Appendix 9, the equation I get is fx squared over 6 EI x minus 3L. If I take the EI that's sitting over here, bring it to the other side, I get exactly the same equation except for a minus sign. Okay, and I have basically chosen to say that positive is down. In the book, positive y is up. So there's a sign difference between my answer and the book's answer, because I called a positive deflection down, they called a positive deflection up, but I have just derived using Castigliano the deflection at anywhere within a cantilevered beam. Next problem. Let's calculate the deflection at the end of a cantilevered beam with a distributed load rather than a point load. Now I've got the dummy load Q sitting here, so I guess what I'm going to do is calculate the deflection everywhere within this structure, not just at the end. So I'm going to use my dummy load Q. These things would be the answer as given by the appendix in the back of the book. I just put this bending energy equation right here for reference. Now I am going to measure, I say this is the simple problem because I'm going to measure my X from the free end and X pointing left. And so when I want to calculate the moment at any location, so I'll put my mouse right there and I want to calculate the bending moment there, I'm going to get a bending moment that comes from both Q and the distributed load, and my bending moment will have two terms, a Q term and a distributed load term. And at this point where my mouse is, I would have a Q times X term, and I'm going to have a WX squared over 2 term, WX squared over 2 term, and a QX term, both of them added together. And that's the only equation I need because I don't have any other point load popping into this thing. So it's just one region that I have to deal with. Here's my moment. Now I want to calculate, okay, I do remember what I'm doing. I am calculating my deflection at the end of this beam. But okay, I misunderstood for a moment what I was doing. I'm calculating the deflection at the end, but there is no load at the end. There is no F at the end. I can't take my partials with respect to W. That would be meaningless. Since there is no load at the end, I want to know the deflection at the end. I place the dummy load Q there. Now I've written my moment in terms of W and Q. I can take my partial of the moment with respect to Q, and my partial of the moment with respect to Q gets nothing out of this term, and it gets an X out of this term. So partial of moment with respect to Q is just X. My EI deflection equation is the integral of moment times the partial of M with respect to Q dx. And I'll get an answer, but from that answer I'll substitute Q equals 0 and I'll get that term. Now again, just to fill in the blanks a little bit, my this thing says take my moment, which is Wx over 2, X squared over 2 plus Qx. Yeah, something's a little bit, okay, I wrote this badly. That has to be Q times X. Got an error in there actually that didn't hurt anything. Wx squared over 2 plus Q times X. Multiplying the partial of M with respect to Q, that's just X. Do this integral, substitute Q equals 0, and I get that answer. Now, I can do it even easier. Rather than taking the full moment that involves Q, right now I can set Q equal to 0. After I've taken my partial, with Q equal to 0, this just leaves behind Wx squared over 2 times the partial. The integral of Wx squared over 2 times the partial, which is X, still gives me the same answer. All three of these give me the same answer. They mean exactly the same thing. Okay, and so my deflection at the end of a cantilevered beam with distributed loading is WL to the 4th over 8. The appendix says minus WL to the 4th over 8 EI, but this is EI delta. Move EI to the other side, and we have a perfect match. Next problem. Calculate the deflection anywhere within this distributed loading. Okay, so Q is no longer stuck to the end, so that I can only get an end deflection. Q is going to be located anywhere within the beam, located by a quantity that I'm going to call A. And here is the answer for the deflection everywhere. We should be able to match that. Now, what I'm going to have to do is write the bending moment everywhere within the beam, but because of that point load, I'm going to have two terms. One term on to the right of the point load and a term to the left of the point load. In region 1, my moment in region 1 is going to be Wx squared over 2. at any point within this region, it's wx squared over 2. The derivative of my moment in region 1 with respect to q is 0, since there is no q in that term. In region 2, after I've passed q, my moment is still wx squared over 2, but I get another term when I look to the right, which is q times this distance to my mouse. And that distance to my mouse is x, which is my distance all the way back to the right-hand end, minus a, because a is the location of load q. So I get my original term, wx squared over 2, acting in a clockwise direction, and q also acts in that same direction, so that's a q times x minus a. The partial derivative of this thing with respect to q is x minus a. Partial of m2 with respect to q, MathCAD says, is x minus a. Now, the other thing I'm going to ask MathCAD to do is calculate m2. Now I can substitute q equal to 0, and of course I'm going to get just wx squared over 2 when I substitute in q equals 0, but I'm showing you the notation for that. This is a moment 2, but substitute q equals 0 and symbolically tell me the answer, and there it is. Let's look at the answer done 3 different ways with 2 different ways with a couple of different powers of MathCAD acting. Region 1 has moment 1 times the partial of moment 1 with respect to q. But this quantity was 0, so there's not going to be any contribution there. And that region goes from 0 to a. A is where q was applied. The next term goes from a to l, and that's going to be moment in region 2 times the partial of moment in region 2 with respect to q. There's that integral. After the integrals are done, I'll substitute q equals 0 and get that. Or I can say EI delta, and now I'm going to plug in m1 as just the wx squared over 2. The derivative is 0. m2, after I've substituted in q equals 0, m2 is wx squared over 2, and my dm2 dq is x minus a, so I multiply by x minus a, although again I've got a appear to have a typing problem there. It seems like I need I'm not sure why there's not a parenthesis showing up there. There was a parenthesis there, I just couldn't see it. Okay, let's see. That looks a little different. Hang on a minute. Well, certainly that is not the same as that. I certainly need the parentheses. Type of parentheses. Oops, Control Z. Type the parentheses. Control Z. Select both. Type the parentheses. And now it's already there. Okay, I'm going to retype this term. I'm just puzzled. And it really should come out to be the same thing. We'll get rid of all of that term. Times parenthesis x minus a parenthesis dx. And it's looking different. And maybe I just need to do a simplify on it. I don't know why it's looking different. Actually, I'm going to pause and figure out what's going on, then I'll restart the video. Okay, I've resumed the video, and I certainly did need the parentheses, and to make them look the same, I'd used a symbolic tool called expand, and it just expands out some of those fractions, and then we see that they are exactly the same. But I can't compare this answer to this answer because this answer measured x from the left. My answer is measuring x from the right. So I need to, again, to do a change of variables. So if I take my EI delta quantity and I substitute a is equal to L minus x and expand it and then symbolically figure out what I've got here, this is it. And if I take the answer wx squared over 24 EI, wx squared over 24, I'm leaving the EI out, 4lx minus x squared minus 6l squared, 4lx minus x squared minus 6l squared, and if I expand that algebraically, I get this, which compares perfectly to that, which means I have correctly derived this deflection equation as measured from the left-hand end. And certainly if I plug in if I plug in L for X in this one, I will get this quantity right here. So again, dummy load has been used to calculate an equation for the deflection everywhere within this beam. Looking at another one, this is a simply supported beam, two simple supports with an overhang, and there is a load applied out at the overhang. Now on this one, whether I'm going to be setting X from left or right doesn't matter, but I am going to have to end up doing some statics. I'm still going to choose to measure X from the right hand side, but when I get into this region measuring X from the right hand side, I'm going to need that reaction R2. So for the first time I've got to do some statics. So what I'm going to do for my statics is I'm going to calculate R2 in terms of the applied load in the geometry by summing moments about point A. If I sum moments about point A, I'm going to get a moment R2 times L, and I'm going to get a moment minus F times L plus A. R2 times L minus F times L plus A. This is my sum of moment term. I'm setting it equal to 0. Now that I've set my sum of moments equals 0 equation, I'm asking MathCAD to solve for R2 from this equation, and it gives me FA plus L over L for the value of R2, and then I'm taking this value and sticking it into R2. Sort of a long, complicated looking MathCAD thing, but I hope you agree this is the sum of moments set equal to 0. Solve for R2, which you could do trivially, and then save the new symbolic answer in R2. Now what I can do is, again, starting from the right, I'm going to have two different regions for the moment because of that point load. My region between these two loads will say my moment is nothing but F times X, where X is measured from the right. And because I want to calculate the end deflection, and only the end deflection, and there's already a load there, I'm going to take my partial of my moments with respect to F, the load that's already there. And my partial with respect to F is just X. There it is. In the second region, I'm going to have a moment because of R2, and I'm going to have a moment because of C. And my moment equation is going to be R2 times X minus A plus F times X. Now, my moment in region 2 includes every term that was in region 1, F times X, and that didn't change. I'm just adding a new term, R2 times X minus A. So a way to write this in MathCAD, which is fairly simple, is to say moment 2 is all the moment 1 stuff minus R2 times X minus A, because the R2 moment is in the opposite direction of the F moment. Okay, and so my moment 2 being that. But if I expand out moment 2 really is Fx plus, and it did a little bit more, R2, which is Fa plus L over L, Fa plus L over L, F A plus L over L, multiplying by X minus A minus X, minus sign, so X minus A became swapped, minus sign became a plus. This, in MathCAD, computes to all of this. If I take the partial of all of this with respect to F, I'm going to get an X plus all of this stuff with the F taken out. X plus all of this stuff with the F taken out is derivative of M2 with respect to F. MathCAD does that for me. Take this symbolic answer, stuff it into that variable. Now when I'm ready to calculate my deflection, I just need to integrate the moment in region 1 times the derivative in region 1 plus the moment in region 2 times the derivative in region 2. Moment, derivative, moment, and derivative. This thing is going to have this long term multiplied by that long term. It's all encapsulated right here. Do the algebra, multiply things together, do the integration with respect to X. When you do all that, you come out with an FA cubed over 3 plus FLA squared over 3. The appendix says the deflection at the end of this thing is FA squared over 3EI L plus A. Let's see, I think earlier, let's see, if we pull out the FA squared and the 3 from both terms, okay, FA squared over 3, that's going to leave an A behind here, and that's going to leave an L behind here, FA squared over 3, L plus A, EI, bring it back over, matches that EI down there. These things are identical, okay, except for the sign. So I've used Castigliano to calculate the deflection of a simply supported beam which has an overhanging load, F, out of the end, and I've only calculated the end deflection. What's the next thing that we could do? Let's calculate the deflection everywhere. To calculate the deflection everywhere, I need a dummy load that can be moved everywhere. This one's going to be a little bit harder because I'm definitely going to have one equation for the deflection in the range BC. I'm going to have a different equation in the range AB. What I'm going to do is calculate the BC deflection equation by placing Q within the range B to C. With the Q in the range B to C, the deflection equation I come up with is only good for deflections in the range B to C. Okay, and now that I've added Q, I'm going to have to recalculate the statics for R2. So let's do that first. And so what I've said here is I'm using a dummy load, and because A is already taken in this picture, there's that's this distance between B and C was called A. I'm going to use a variable D, which tells me how far Q is from the right. So dummy load located the distance D from the right. I've got to redo the statics for R2 because I now have the load Q here. To be careful with MathCAD, I've already defined R2 to be a symbolic thing. It has value, and if I say R2 symbolics, that's what our R2 is, left over from an earlier problem. To clear that out, I'm going to say R2 colon equal R2, and now when I say R2 symbolics, it says R2. R2 is nothing at this point. So I'm just R2 equal R2 clears it from the previous solution. Now, my statics, I'm going to sum moments about A, and when I sum moments about A, I'm going to get a contribution from R2, and from Q, and from F. The R2 contribution will be in the opposite direction of the other two, and it'll be an R2 times L. It'll be an F times L plus A, and it's going to be a Q times the total distance L plus A minus D. So, sum of moments about A is going to be F times L plus A, plus Q times L plus A minus D, plus R2 times L. The sum of all of those moments must equal to 0. R2 shows up in this sum of moment equations. I'm going to solve this equation for R2. That's the instruction given right here. And when I solve this equation for R2, I'm going to get this term that involves A and D and L and F and Q. And I'm going to take this symbolic term and stuff it into the R2 variable. Now that I have that, I can start writing my moments. And I've got to write moments in 3 different regions, between F and Q, between Q and R2, and between R2 and A. 3 different moment terms, 3 different partials. The moment in region 1 is nothing but F times X. F times X. Now, since I want to calculate the deflection at the place of Q, I'm going to take my partials with respect to Q. What is the partial of M1 with respect to Q? Nothing. I'm going to create a variable dm1 dq, which is the partial of m1 with respect to q. MathCAD says it's 0. Moment number 2 will be in the region between R2 and Q. I'm still going to have my F times X moment. So I can say that moment number 2 starts off with moment number 1, okay, and it adds in a Q term in the same direction as the F term. And this quantity Q is going to be located a distance, or when I make my cut here, the distance between my cut and Q is going to be a distance X minus D. So moment 2 is moment 1 plus Q times X minus D. MathCAD says that's this. Okay. I will create a new variable called M2Q0, which is different than M2. It's nothing but M2 when I substitute in Q equals 0. Well, if I substitute in Q equals 0 for M2, what do I get? Fx. So M2Q0 is just Fx. I'll use this to save some time later. But I got to take my partial with respect to Q of all of this, and my partial with respect to Q of M2 is going to be D minus X. No, minus D minus X, or X minus D. Same thing. There's my partial in that one. Now, in my region 3, I still have all the stuff that caused moments before, so the moment in region 3 is the moment equation in region 2 plus an R2 term. Moment in region 3 is moment in region 2. And my R2 term is in the opposite direction. And this quantity, the distance, the moment arm at any cut point in here is going to involve a distance x minus a. So moment in region 3 is the moment in region 2 minus R2 times the distance x minus a. Substituting the definition of M2 right here and doing all of that arithmetic, this is the moment in region 3. I think you can appreciate we're really going to enjoy setting Q equal to 0 to clean this up some. And so if we take the moment in region 3 and substitute Q equals 0, the moment in region 3 with Q equals 0 simplifies down quite a bit. But I've got to take my partial of the moment in region 3 before I eliminate Q. Otherwise there'd be nothing left. There is no partial of this with respect to Q, but the partial of this with respect to Q is nothing from this term, a minus d minus x from this term, which is an x minus d, and then this term times that term times that term, all divided by L. I'm sorry, this term times that term divided by L would be the partial with respect to Q. That gives us this term right here. This is the derivative of moment region 3 with respect to Q. Now, my deflection equation at Q is going to have 3 different terms because of the 3 different loads. I'm going to have a term that goes between 0 and x equals 0 and d. Then another one's going to go from d to a, and the other one's going to go from a to L plus a. First region, 0 to d, is M1 partial of M1 with respect to Q. That was a 0, and so this term being 0 makes this term irrelevant. Then I'm going to have M2 times the partial of M2 with respect to Q. Here's M2 that still has Q in it. Partial of M2 with respect to Q, that's x minus d. Then finally, a term that goes from a to a plus L of M3, this big thing still has Q in it, times the partial of M3 with respect to Q, that's this term right here, multiplying by it. Okay, take this integral, solve the integral, substitute Q equals 0, simplify it. That's what you get algebraically. I'm skipping a whole lot of calculus, but I don't need to teach you calculus. You've had calculus, 3 different calculus classes probably. Now, this is done sort of maximizing MathCAD notation. Let's do it a little differently. Let's take M1. First of all, this term right here is still 0. This is an irrelevant term. But rather than taking M2 right here, which still involves Q, I'm going to use the M2Q0, which is just what I get out of this thing when I set Q equal to 0. That's just going to be Fx. So this M2Q0 is Fx. dm2dq, though, is still x minus d. So this is Fx, this is x minus d. And then here M3Q0 says take my moment 3, but set Q equal to 0. M3Q0 multiply, so I set it equal to 0 early here, times the partial of M3 with respect to Q. Now I've already set Q equal to 0 in these terms. There's no need then to substitute Q equals 0 later. I've already done it before I even write the terms down. Simplify it, do the integral, simplify it. You get the same thing. You can either substitute Q equals 0 late, or I can substitute Q equals 0 when I write out the equation, and I get the same thing. Maybe one other thing that I want to do here, just to show you maybe a little more completely what I'm doing, is another version, but I go grab M1 is Fx, copy and paste. dm1 dq is 0, copy, paste. That's Fx times 0, nothing in that term. Okay, I grab the Fx, oops, cancel. I grab the Fx, which is M2 with Q set equal to 0. Paste. I grab x minus d, copy, and paste it in for this variable. And then I grab the M3 with Q set equal to 0, copy, M3 Q set equal to 0, paste. I grab the dm3 dq, copy, and paste. Let's clean it up a little bit. Alright, notice that answer hadn't changed. If you were writing this out by hand, what you would be writing out is the integral from 0 to d of f times x times 0. Then you would write out the integral from d to a of fx times x minus d. Then you would write out by hand integrating a to a plus l of the moment 3 with q set equal to 0, multiplying the partial of moment 3 with respect to q, all of that stuff. Now, what I'm still leaving out is multiplying all of these terms together so that I can get an interesting polynomial in x. I didn't do that algebra. MathCAD did it for me. I didn't even do this little bit of algebra. MathCAD did that for me. But when you do that algebra, integrate, apply the limits, you get this stuff. That's what all this MathCAD shorthand is doing. Okay, and so at this point I'm really using the high-level concept of moment times partial, and this form hides all that algebra that you will have to do by hand when you work problems. But I just want to make sure you understand this is the same as this, is the same as this, and I'll be using again more of this notation and less of this notation as we go on, because you don't need me to actually do the algebraic substitution that m2 is fx and the derivative is x minus d. You can do that substitution yourself. Okay, let me get rid of what I just did here and clean my document up a little bit because I don't want to mess it up. Now, again, if I do a change of variable to take into account that the textbook measured from the other side, so I'm substituting d with L plus a minus x, I get this equation for the deflection as a function of x measured from the left, where this was the equation for deflection where d is the distance from the right. And I compare these two, and I've got an fx minus L over 6, fL minus x over 6, but there'll be a minus sign change somewhere. And x minus L squared minus a times that, if you expand all of this stuff out, it in fact equals the negative of that. And that is a match, and so I've now derived the equation for the deflection of a simply supported beam with an overhang, with a load at the end, but I've got the deflection everywhere I want at any x value. Actually, what would be interesting would be to plot this, and I think I will do that real quick just for fun. So let's see. Nope, changed my mind. I'd have to assign numbers to everything. Okay, but this equation is only in the region BC. So this is the same picture. This is only in the region BC that I've matched. I haven't calculated the deflection in the region AB yet. So the next thing I'm going to do is calculate the deflection in the region A to B by placing the dummy load in the region A to B. There are some things that are going to change. The statics probably doesn't change because everything that I wrote about sum of moments was true. Statics doesn't change, but my moment equations will change and my regions will change. Okay, but again, main thing I'm changing is Q is now in the region A to B, but Q is still measured from the right hand side by a variable called D that tells me where Q is. My moment in region 1 is just f times x, and the partial of that with respect to Q is 0. My moment in region 2 is the moment in region 1 minus R2 times x minus a. Moment in region 2 is the moment in region 1 minus R2 times x minus a. Okay, but because I'm bringing in the quantity R2, and because the static says R2 in terms of Q and other stuff is that, there's no change. But when I substitute in the value R2, this stuff, to there, it gives me a fairly long and ugly expression for moment in 2 involving Q. What I'm going to do is take the partial of that with respect to Q. I get the terms I expect. Now I can set Q equal to 0 in this equation and get this. M2Q0 is M2 with Q set equal to 0, and it's that simpler term. That'll make the math easier. My moment in region 3, now that I've gone past Q, is still going to be all these terms from the right still in effect. So my moment in region 3 is the moment equation from region 2 plus a Q term, and that Q term is going to be L plus A minus a distance L plus A minus D away. Let's see, is that right? No, it's going to be X minus D. The distance between my mouse and Q is X measured from the right hand end minus D, which locates Q. So moment number 3 is moment number 2 plus Q times X minus D. Something looks funny there. That should have a parenthesis. Don't remember when that happened, but I'll go ahead and fix that. Type that parenthesis. Here is my M3, and it involves the M1 term, and it involves the M2 term, and finally it involves adding in another term. My derivative with respect to Q, that, and now I can take my moment 3 equation, substitute Q equals 0, and I get a much simpler equation when that Q term goes to 0 and that Q term goes to 0. Now with my moment and my partials all done, working sort of at the easiest high level, the deflection in the direction of Q because of load Q is the integral over region 1 of M1 and the derivative plus the integral over region 2, which goes from region 1 is 0 to A, region 2 is from A to D, and region 3 is going to be from D to L plus A. So region 2, A to D of moment 2, partial of Q. Region 3, D to L plus A, moment 3, partial of moment 3. Haven't said Q equal to 0 using M1, M2, and M3, so I've got to ask it to substitute Q equals 0 and then simplify it, and I get this. Or I can say integral moment 1 dm1, but this one was 0, so I didn't bother with this one, plus M2 with Q already set to 0 times the derivative, plus M3 with Q already set to 0 times the derivative, means I can leave off this substitute step and just do a simplify, and I get exactly the same thing. I could, of course, go through and write another version of it where instead of typing M1, I would type FX. Instead of typing dm1 dq, I would type a 0. Instead of typing m2q0, I would type that. Instead of typing dm2 dq, I would type that. But there's no reason for me to do all of that typing, just to show you those direct substitutions of those terms. That is what you would have to do by hand, and then you'd have to do some multiplication of polynomial terms, and then you'd have to do some integration, but that's just math you've done before. Now, this answer gives me the deflection everywhere in the range between A and B, presuming that I'm a distance D from the right-hand end. But that's not what's in the book. They're presuming that the place where I'm calculating my deflection is a distance X from the left-hand end. So if I take my equation and do a substitution where D is substituted as L plus A minus X, and I simplify it, I get the deflection as AFX, L squared minus X squared over 6L, FAX over 6, there's the FAX over 6 EIL. We'll bring the EI over, and we have a 6 EIL in the denominator, L squared minus X squared, L squared minus X squared. And so I have a minus sign, and they have a positive sign, to be expected, because I defined positive as down, they defined positive as up, and so we ought to disagree on the sign, but otherwise I've matched their term. Now we'll look at a statically indeterminate problem. The statically indeterminate problem is a cantilevered beam with a distributed load, but there's an end support here. There's a little triangle of support right here. which causes the deflection at the end of this beam to be 0. So I said I'm going to solve this statically indeterminate problem, cantilever beam with end support, but I'm going to do it the hard way because I know what's hard and what's easy because I played with this before. I'm going to do it the hard way because for the first time I'm going to measure X from the left. I'm going to measure X from the wall. That's going to mean I've got to do some statics that I haven't had to do before. Okay, then the other thing I say is notice that there are 3 reactions, M1, R1, and R2. M1, R1, R2. That's what makes this thing indeterminate. Okay, what I can do is, of those 3, I can treat any one of them as if it was an applied load rather than a support. And I can pick any one that I want. I think R2 is probably the easiest to pick. R1 is the second easiest to pick. What I'm going to do is pick M1 as my redundant reaction. And if I could get rid of this moment for a little while, what would my structure really be? It would be a simply supported beam with a distributed load all the way across. Now when I treat my moment as just an extra load, then it becomes a simply supported beam, distributed load all the way across, but also it has an applied concentrated moment at one end. That's the way I'm going to view this thing. Okay, let's see. Actually, that's what I thought I was going to do, but maybe I didn't. I may have gotten ahead of myself here. There's so many different ways to do this one. Where are my moments? It says for this problem treating R2 as the applied load, measuring X from the right is by far the easiest way, but I'm not going to do that. Instead, I'm going to let M1, my support reaction, behave as if it's my applied load. That's the harder way to do it. Next page I'll do the easier way. So first of all, if I'm going to measure from the left, then I'm going to have to do the statics that I can. Now what I'm going to do is treat M1 as a known moment, and R1 and R2 are the unknown things. Since I'm measuring from the left, I only need R1. I'll never need R2 in an equation. So for my statics, I'm going to sum moments about the left-hand end. I'm first going to clear out R2 and M1 that I used in previous calculations. And so this is my sum of moments about the left-hand end. And the sum of moments about the left-hand end about this point will be M1, and I'm going to call that positive. Since R1 passes through the left-hand end, it doesn't make a contribution to this moment equation. Let's see. Yeah, it doesn't make a contribution to the moment equation, but W does create a counter moment, a moment in the opposite direction from M1, and that moment will be WL squared over 2. So I've got an M1 countered by WL squared over 2. But finally, way out here, R2 makes a moment in the same direction as M1, and that'll be R2 times L. So M1 minus WL squared over 2 plus R2 times L. That's sum of moments about the left-hand end. Set it equal to 0. With that set equal to 0, solve algebraically for R2. What do you get when you solve that for R2? You get this. Take this, stuff it into the variable R2, and keep it handy. Now the second step will give me R1, which is what I was after all the time. And so R1, I'm going to just use sum of forces in the y direction to calculate R1. Sum of forces in the y direction will be R1 plus R2 minus WL. R1 plus R2 minus WL. Sum of forces in the y direction equals 0. Use that equation to solve for R1. Solving this for R1, we get this stuff. Stuff it into the R1 variable. That's just the statics. Now that I've done my statics, at least for R1 in terms of M and other stuff, I can now make my cut anywhere in the middle of the beam. I'll set my mouse where I want to make the cut, and then looking left, my sum of moments about that point will be a term that involves my applied moment, a term that involves R1 in the other direction, and a term that involves the distributed load in the same direction as M1. So my moment in region 1 is my applied moment M1 minus R1x plus WX squared over 2. And I ask it to symbolically evaluate that, and what happens when it does is it takes this R1 right here and replaces it with all of that stuff. You'll need to do that. because that's going to get R1 written in terms of M1. So I do need to do that substitution, and here is the results. Notice R1 does not show up in this expression. R1 has already been substituted with this term right here. Now here is my moment, and I only have one region. So my derivative of my moment with respect to what? I'm going to take the derivative of my moment equation with respect to the variable that I eventually want to solve for, and that's M1. So I'm going to take the derivative of my moment with respect to M1. The derivative of my moment with respect to M1. The derivative of this entire thing with respect to M1 is going to give me a 1 right here, and looking for M1 in here, it's going to give me a 2x over 2L with a minus sign, and that's just going to be a minus x over L. So here's my derivative of M with respect to M1. Okay, now this is important. Remember earlier in the notes we said when we take derivatives with respect to forces we get deflections, but when we take derivatives with respect to moments or torques we get slope angles, or we get slopes, not slope angles, we get slopes. So instead of saying EI delta here, I'm going to say EI slope is my integral over the entire structure of, and this is my energy term, okay, moment times the partial of moment with respect to the applied moment. Okay, it does the integral and gives me this. Now what's sitting in this term for M? All of that. What's sitting right here? That little bit. Okay, and so presumably, just to show you that it's still true and to show you more what you would type by hand or write by hand, I'll go ahead and do this, and I'm going to replace M with all of this stuff. It's a little hard to see. Yes, I'm going to replace M with all of that stuff, and I'm going to replace the derivative term with that. Okay, and if I have done things right, then this notation, which is very compact, this is what you would write out by hand. But for you to do this integral, you would have to take this polynomial and multiply by this and just figure out a way to collect all the x terms and then integrate those polynomials. And once you've integrated the polynomials, then you have to apply the limits to the values, and when you've done all of that stuff that I'm not showing and don't need to show you, you end up with this, which is exactly what I ended up here with the more compact notation. Okay, this is at the concept level, this is getting closer to the detail level, but there's some arithmetic to do here. I'm going to erase that piece right there. Now this gives me my slope at this end that is written in terms of the distributed load and the applied moment. Okay, and if I change the moment, I change the slope. Now I'm not going to set this M1 is not a dummy variable. I'm not going to set it equal to 0. That makes it disappear, and that would give me, if I did that, that would give me the slope at the end of a simply supported beam with a distributed load, and of a simply supported beam, not a cantilever beam. That give me the slope at the end of a simply supported beam with a distributed load. Okay, but the true purpose of this moment is to enforce a boundary condition that says the slope at this end is 0. Okay, so if I've got the slope, if I've got a slope equation that depends on moment, then I ought to be able to take this slope equation, set it equal to 0, and solve for the value of the moment that makes that true. That's exactly what I'm going to do. Using the boundary condition that slope equals 0 at x equals 0, I'm going to solve for that unknown moment. Okay, so I'm going to say slope equals 0. Now, what am I doing? I'm putting this slope right there. Slope equation equals 0. Solve this slope equation for M1. Solve for M1, and it gives WL squared over 8. And stuff that back into M1. So M1 is WL squared over 8. So the reaction in terms of both the applied load and the length of the beam, because the reaction depends on the geometry. Now that I've solved for the unknown moment, I can now actually use statics to solve for the others. And I can, let's see, reaction number one, let's see, let me remember what I did here. Okay, reaction number one I had already solved for, but it was written in terms of M1. So reaction number one written in terms of M1, but I'm going to substitute WL squared over 8 for M1. So if I take this thing, substitute M1 as WL squared over 8, I get 5LW over 8. Then if I take R2, which I did solve for up here, R2 was that, but it was written in terms of that unknown M1. Now that I know M1, I can take the R2 reaction, substitute M1 as WL squared over 8, and I get 3LW over 8. If I go to Appendix A913 and the reactions, actually I don't need x equals 0, it tells me that the reaction 1 is 5WL over 8, exactly what I got. Reaction 2 is 3WL over 8, exactly what I got. And that moment 1 is WL squared over 8, exactly what I've got. So all I've done so far is use Castigliano to calculate all three static reactions in an indeterminate structure. I haven't done any deflections or anything else. I've used it to calculate, first of all, by making it appear to be statically determinate by pretending that M1 was just a load and not a reaction. I solved for slope as a function of M1. Then I said slope equals 0 because of M1. Solve for M1 that makes the slope 0. Did that right here. Where was that? Did that right here. Slope equals 0. Solve for M1 to make slope 0. What I effectively did was set this equation equal to 0 and solve for M1. Then I could substitute in the new value of M1 to all the other reactions. Let's do the same problem, but I'm going to do it the easy way, because I in fact believe that measuring x from the right and letting R2 be the redundant reaction says what I have here is a cantilevered beam with both a distributed loading and an end-load. But later on I'm going to find the deflection because of W and R2, set that deflection equal to 0, because that's the purpose of R2, is to keep that deflection equal to 0, and I'll be able to solve for this unknown R2. It's going to be much easier. First of all, since R2 is the redundant reaction and I'm going to be measuring from the right and looking right, these two reactions will never come into it. No statics necessary to solve for R2 properly from here. I am going to have to do some statics to get M1 and R1 later, but I don't need it to solve for R2. And so I'm going to be cutting at any point x within the beam, x measured from the right, and my moment will have an R2 piece and a W piece. So my moment equation with x measured from, oops, I said left, x measured from the right. My moment is R2 times x. If I'm over here, R2 times x, and then minus Wx squared over 2. Minus Wx squared over 2. There's my moment. The partial of my moment with respect to what? Well, I want to get the deflection that's influenced by R2, so I'm going to take my partial with respect to R2. So the partial of my moment with respect to R2 is just going to be x. Partial of moment with respect to R2 is just x. Now that I've done that, and again I only have one moment equation, then my EI deflection, why not theta? Because I'm taking partial with respect to a straight line load. So now we're back away from slopes, we're back to deflections. EI delta is the integral over the entire length of the moment times the partial of moment with respect to R2. Here's the moment. Here's the partial of moment with respect to R2. So we would simply take this equation, put it here, take that x value, put it right there, multiply, massage, integrate, and here's what we get for the deflection. And what does this mean? This is a deflection of a cantilevered beam with a distributed load acting downward and a point load at the end acting upward. But that's not the real beam. A real beam actually has a support, but what effect does that support have? It causes an R2 force, no doubt about that. But the R2 is just sufficient to cause this deflection at that end to go to 0. So I'm going to solve that. deflection equals 0, solve for R2. That's equivalent to solving this thing for R2 when I set this equal to 0. And I get 3LW over 8. Okay, but notice from the previous problem, R2, 3WL over 8. I got that one directly. The Castigliano is over. Now if I want M1 and R1 from this one, I'm going to have to do a little bit of statics. So we need statics to get M1 and R1. And so what I'm going to do to get M1 is some moments about the left-hand end. And the moments about the left-hand end will not involve the R1 term. Moments about this left-hand end will be a WL squared over 2 acting in one direction and R2L acting the other direction. WL squared over 2 is positive. R2L is the opposite of that. I'm going to take this. So this is M1. Okay, I'm not summing moments about the left-hand end. Let's see. Okay, I'm saying that M1 must equal the effect of all these other moments is what I said. But I do need to substitute in for the R2 term. I need to substitute in 3LW over 8. So when I substitute 3LW over 8, I get WL squared over 8 for M1. What did I get before? WL squared over 8. That's comforting. Now that I've got M1, I can calculate R1 simply by summing forces in the vertical direction, and I'm going to have R2, which I now know acting upward and W acting downward, R2 acting upward, W times L acting downward, and I get R1 as 5LW over 8, which is exactly what I get out of the appendix. This, I believe, was a whole lot easier than the previous solution, which gave me exactly the same thing. Okay, now the hardest problem of all and the last problem is I want to calculate the deflection everywhere within this indeterminate structure. I want the deflection as a function of x. To get the deflection everywhere, I got to be able to get it anywhere. To be able to get it anywhere, I've got to have a point load. So I'm going to apply a dummy load Q, located at distance A from the right-hand end. I will work from the right because it's easier, meaning I don't have to do all of this statics in terms of Q. And so I can proceed with no statics right away, writing moment in region 1. Then I'm going to have to write the moment in region 2. The point load forces me to change equations. My moment in region 1 is going to have an R2x term, and it's going to have a WX squared over 2 term in the opposite direction. R2x minus WX squared over 2. Okay, and that gets stored in M1. And then I'm going to calculate the derivative of M1 with respect to what? With respect to Q, because I want to know the deflection at point Q. The derivative of M1 with respect to Q is what? I've got an X. What have I got here? I have typed the wrong thing. Oh, I'm sorry. I got ahead of myself on this problem. Before I can calculate, yeah, this is actually very important. Before I can calculate the deflection at Q, I've got to know how this reaction varies with Q. And I haven't solved for that yet. I've got a brand new clean problem. I cannot use any of the work that I've done earlier. I've got to start over. Step 1, since it's an indeterminate structure, is solve for R2 as a function of Q. And then I can solve for deflections at Q. So that doesn't change anything about my moment equation. It's just that with two different problems, one is solve for R2, one is solve for the deflection at Q, I'm going to have to take two different partials. One partial with respect to R2 and a different partial with respect to Q. I'm going to do all of those ahead of time. So first thing I'm going to do, dm1 dr2 is the derivative of m1 with respect to R2. Looking back at this, derivative of m1 with respect to R2 is just an x. There it is. The derivative of m1 with respect to Q, derivative of m1 with respect to Q is a 0. There's no Q there. That's a 0. Now, m2 is going to be in this region, and I have two regions, 1 and 2. M2 is M1. Everything that was true in region 1 is still true in region 2. It is M1, Okay, but I've got Q acting in the negative direction, just like Wx squared over 2 is acting in the negative direction. So M2 is M1 minus Q. How much is Q? Q is X measured from the left end minus A. A is the distance from left end to Q. So M2 is M1 minus QX minus A. All of that plugging in the M1 stuff here brings along these terms right here plus the new term. That's just a little bit of MathCAD shorthand. Okay, so I just don't have to retype these terms. It just lets them fall on down. Then I'm going to take the derivative of this M2 with respect to R2. What is that? Looking carefully, there's only one term, X. Derivative of M2 with respect to Q, there's only one term, A minus X. Derivative of M2 with respect to R2, X. Derivative of M2 with respect to Q, A minus X. Now, remember the rule. When we do have a true dummy load, I can set the dummy load equal to 0 as soon as I've taken the partials. So if I take M2, which does involve Q, then I can now set that Q equal to 0 and lose this term, and I have these terms left behind. So if I take M2 and substitute Q equals 0, these two terms together are simply these two terms. MathCAD made it look a little bit differently. That term is dropped off here. Now, what I'm going to do in this fairly compact MathCAD notation is I'm going to set the deflection at the right end equal to 0 and solve for the R2 in terms of W and Q. This compact MathCAD statement is going to do that. So let's see where all of that happens. Okay, actually it's going to take two statements to do it. This is the deflection at the end of the beam because of R2. To get that, I've got to use my moments and my R2 derivatives. Moment 1 times the partial of moment 1 with respect to R2. Moment 1 partial with respect to R2. There is a term there. And then in region 2, it's moment 2, right there, times the partial of moment 2 with respect to R2. It's that X term. This one is maybe worth typing just to show you it gets the same thing. So I'm going to copy and paste. Let's move it up a little bit so it doesn't interfere quite so much. And M1 is this. Copy. That's M1. dm1 dr2 is just X. So I'm going to change that into an X. M2 is, let's see, still haven't set, okay, we don't want to set Q equal to 0. M2 is this. Copy and paste. dm2 dr2 is just X again. Copy and paste. What you would write, oops, I pasted this in the wrong place. Copy, paste. What you would write is the integral of this times X plus integral of that times X, and you would have to then multiply, generate the polynomial, integrate the polynomial, apply the boundary conditions, multiply, simplify, collect terms, integrate the polynomial, apply the boundary conditions, and when you did that you would get all of this stuff. And again, I'm not showing you the algebra of the multiplication, and I'm not showing you the calculus of integrating a polynomial because you know how to do that, and I'm not showing you how to apply the limits of integration because you know how to do that too. But all of this short MathCAD stuff, and I want to restore this one to M1 times dm1 dr2, and of course we're getting the same answer. Now what do I have here? Because I took my derivative with respect to R2, I have the deflection at the end of a cantilevered beam that has both a distributed load, an end load, and an intermediate load. End load acting up, intermediate load acting down. and I would expect my deflection then to be in terms of R2, W, and Q. And it is. It involves R2, it involves W, and it involves Q. Okay? And so now what do I want? I want my real value of R2, because this is the indeterminate, this is really a support here that causes deflection to be 0. So since the purpose of the support is to provide enough R2 to cause the deflection to be equal to 0, I'm going to set the deflection equal to 0 and solve for the R2 that makes it happen. Here's my deflection equation. Set this thing equal to 0. Okay, and I'm going to, again, do this a little differently. Make a little room. Paste that in. And set it equal to 0. And now that I've set it equal to 0, I'm going to come over here to the symbolics, and I'm going to solve this thing for R2, and I'm going to get that. This, and what that means is I simply collected all my R2 terms, and you're going to have to do that. R2, R2, I did the algebra to collect all of my R2 terms, and leave R2 on the left and bring everything else to the right. Just do the algebra. When you do that algebra, this is what you get. Let me Control Z out of that. Just get rid of some of this stuff. Put it back the way it was. Okay, so this is the shorthand way of saying it. Take EI delta R2. That's all of this stuff. Set it equal to 0, just like I did a second ago. Now that I've set it equal to 0, solve for R2. It gives me all of that stuff, and I stuff it back into the variable R2. Now what I have is the reaction force R2, but notice it's still written in terms of Q. I need that. I need R2 to be statically consistent with the value of Q. Now I can take the next step. These integrals were for the purpose of dealing with finding the magnitude of the redundant R2. Now I'm going to do my other integrals using partials with respect to Q to find deflections based on Q. And so my deflection at the point by Q is region 1, M1, derivatives with respect to Q, plus region 2, M2, derivatives with respect to Q. And I get that. This is my deflection at point Q, and notice I haven't set Q equal to 0 yet. If I move that a little bit, if I take this thing right here and I set Q equal to 0, a bunch of terms are going to drop out, right? And they do, in fact. So when I take that EI delta Q and substitute Q equals 0, a whole bunch of terms drop out. This is my deflection equation for a cantilevered beam with an end support. So it's a redundant structure or an indeterminate structure. But here's the deflection equation, and it depends on the only true load that exists, W, and geometry. L, the length of the beam, and A tells me where I'm getting the deflection, because I'm getting the deflection at Q, but Q is located a distance A from the end. So the A in that equation tells me where I'm getting the deflection. Now, A is measured from the right-hand end in the textbook. X is measured from the left-hand end. So if I take my equation based on A, right here, and I do a change of variable such that A becomes L minus X. So I'm going to take my EI delta, I'm going to substitute L minus X for A, and simplify it. I get this deflection equation in terms of X measured from the left. And if I go look at the appendix for this problem, appendix 913, I get a Wx squared over 48 EI, Wx squared over 48 EI, and then L minus X, 2X minus 3L, 3L minus 2X. That's my sign change because I said down was positive and they said up was positive. I have derived the deflection of an indeterminate structure, and I've gotten the deflection everywhere within that indeterminate structure. This ends this video. which covers things like simply supported beams and cantilevered beams. The next set of videos that I did last year covers curved beams, and so I'm simply going to ask you, well, let's see, I'll have you take a look at those curved beam videos. I'll do a little bit of an introduction to a curved beam video first. So this ends this segment.